Hello. This is a supplementary video that we put together for a couple of the problems on page 98 of the workbook. They're about transformations, and we had three members of the math team kind of huddled together trying to make sure that we had this right, and we decided, of course, that if we were getting a bit tied in knots over it, that maybe you are too, so let's have a look at it. Before we get into the math, I just want to talk about the general idea of transformations, and what we're going to see here is that sometimes you can do things in a couple of different orders, but if you change the order, it changes the task that you have to carry out. Now, this is a dumb example, but it's the first one I thought of. Let's say you get home and you know that there's two things you have to get done in the next couple of hours. You need to take the dog out for a walk, and you have to cook supper. So, this is me drawing supper, a pot of something, and the dog wants you to take it out for a walk, and there are two ways that you could approach that pair of tasks. One approach you could take is you could take the dog for a walk first and then make supper afterwards. The other option you could go with is you could get supper on first and then, well, here's the thing. Because you took so long to get supper and because you were gone all day, the dog couldn't wait, and now there's been an accident. So instead of taking the dog out, now you must clean up after the dog. Now, both of these kind of take care of the problem technically, and so they both get you the same end result that the dog doesn't have to go anymore and supper is ready, but the order that you did them in meant that you ended up doing different things. This one was walking the dog, this one was cleaning up after the dog. And that's what we're going to see with our math, is that with some transformations, there are two different orders you can do them in, but switching the order also changes what the transformations actually look like. So let's leave this goofy example behind and look at some math problems, and I'll try to show you what I mean here. So what they give us here is they start with a graph of a function, and we're not going to get into what the function is. They're just calling it f of x. And they want us to make changes so that this graph ends up as x equals f of minus y. And the first thing to notice in a situation like this, we're starting with y equals f of x. They want us to end up at x equals f of negative y. There are two paths you can take to get from start to finish. Here, one of them is we'll swap the position of x and y first. So I'm going to say we'll do the x. I'll put a double-headed arrow to mean the swap y. So after we do that swap, we now have x equals f of y. Okay, I just switched the position of those letters, nothing else changed. And now if I want to end up down here, the other thing I need is to put a negative in front of the y, and our notation for that is just y arrow negative y. This means everywhere that you used to have a y, put this instead. So that's one path we could follow, is swap the letters and then put on the negative sign. Another thing we could do is say, all right, down here I have a negative inside the brackets. I'll do that right away. So in that case, what you end up doing is saying where this x is, I'm going to put negative x instead. So our swapped version is, notation first. What I'm doing here is I'm saying where the x used to be, I'm going to put negative x. That means our new version is y equals f of negative x. And now, because I want the x outside the brackets and the y inside the brackets, I do my swap. I do what we call the inversion, where the x's and the y's trade places. And again, I end up in the same spot. So, two different paths, and they both work, but look at the transformations that we did here. This path was switch x and y, meaning do an inverse. And then the y to negative y is what we would call either a vertical reflection, or you could say it's a reflection across the x-axis. I kind of like vertical reflection better. It's a bit more intuitive to me, but this makes total sense too, so whichever you like. That's one path. Invert here, then vertical reflection here. The other path we could have taken is switch x for negative x. That's a horizontal reflection. I'm going to have to write like horiz refl to save space because we're short. Horizontal reflection first, and then we did the inversion after that. So, like in the dog and supper example, there's two different approaches you can take here, but it's not just the same two jobs in two different orders. It's you end up doing different jobs. There's a vertical reflection here and a horizontal reflection here, and which one you choose depends on which sequence you take. So the short answer, the reason this first came up when we were talking about it is, what order do you do inversion in? When you're doing transformations, we tell you to do stretches and reflections first and translations last. Where does inversion fall into that? Where does a function inverse happen? The answer is, it happens with the other reflections, and the order doesn't matter except that what order you choose determines what the other reflections are going to be. So if you do this problem this way and you come out with a vertical reflection, and then the person sitting next to you is doing a horizontal reflection, you're going to say, wait, one of us must be wrong because we aren't doing the same stuff. In this case, you could both be right. It's just that the order that you do them in also affects how the graph ends up looking. So that's the message I'm just going to be hammering on for the next 10 or 15 minutes if you have heard enough of it. I'll show you quickly just graphically what these end up looking like. This path is where we invert the graph, meaning it gets reflected across y equals x. So if we take the original and invert it, we end up getting a curve that looks something like this. And then we reflect it vertically, so our y's become negative y's, and that means we get, from this curve being in the positive y side, it goes to the negative y side, and so this red curve is our end result. If we follow the other path talks about start with x going to negative x, which is what we call a horizontal reflection. I'll go green for this. That would mean instead of this initial curve, we now have a curve that's horizontally reflected. It looks like this guy. And then when we invert that, reflected across y equals x, it lands over here again. This point, minus 5, 0, becomes the point 0, negative 5. The peak here, which is very roughly like minus 2.5, 2, becomes the point 2, comma, minus 2.5. So you can see that whichever path we take, whether we go original to orange to red or original to green to red, we get the same end result. That's another way of showing that both of these paths come out the same. Good? Okay, I'm going to do that 3 more times just in case you want to see more of it. But there's no more new message. It's just going to be hammering away at this with more examples. So, different curve here. So they're starting us with y equals f of x, and they want us to get to x equals f of negative y. In other words, same path as before. And so as before, we have 2 choices. The first one would be put a negative inside the brackets. I'm not sure I'm doing these in the same order as last time, but it'll work out. One of the options is put a negative in the brackets, so you get x becoming negative x. After you do that, your function is y equals f of negative x. Then, to get to here, we have to swap x and y. So if we do our inverse, that's one way it could work. Another way we could do it is to swap the x and y immediately. X and y swap. After we do that, we have x equals f of y. And now the last change we need here is a negative has to appear in front of the y. So where once we had y, we need negative y instead. And that path gets us to the same destination. This is a horizontal reflection. I'm going to say just horizontal reflection from the swapping of x and y, or the x's, and then swapping x and y is the inverse. And here we have x and y swap, that's the inverse. And then y changes to negative y, that's a vertical reflection. So again, we get this effect where you can do two different orders, but the orders are not just changed in order. It's also one has a horizontal flip in it, the other one has a vertical flip in it. And if I do the graphs again, just to reassure ourselves that this really does work, the horizontal reflection takes, let's see, this point is 3, 2. It would become negative 3, 2. This point is 2, negative 3. After horizontal reflection, it would become negative 2, negative 3, and there's a straight line connecting those. And this point over here, which was minus 5, 0, would become plus 5. Sorry, minus 3, 0 would become plus 3, 0. I was thinking that looked too big. Okay, so that's the order where we flip horizontally, and now the next thing we have to do is invert it, meaning swap the x and y coordinates. So on the original curve, we have the point 3, 0. That'll become the point 0, 3. This point is minus 2, minus 3, which becomes minus 3, minus 2. And the point minus 3, 2 would become the point 2, minus 3 over here. Now, I wish I'd connected these as I was going. Let's see. From minus 3, 2, that becomes 2 minus 3. There's a straight line from there to the next point, and then a curve connecting these two. I'm sorry these are sitting right on top of each other. This is not a wonderful example that way. But that's the result you get when you do the horizontal and then the inverse. You know what? It's bugging me how unclear that is. I'm going to run this a slightly different way. That sketch was right, but I want to show you this so that you can actually follow what's going on. Here are the points that are on the original curve. The original contains minus 3, 0. It contains 2, negative 3. And need more space. It contains 3, 2. If I horizontally reflect all those, I get 3, 0, minus 2, minus 3, and minus 3, 2. In other words, horizontal reflection just flips the signs on all the x coordinates. It does nothing to the y coordinates. For the inverse, I swap the x and y's positions, so this becomes 0, 3. They trade places. This becomes minus 3, minus 2. And this one becomes 2, minus 3. So if we do the first path, this is where we end up. Those are our transformed ends, or corners, for the curve. If I do inverse vertical, what do I get? This is the original. I'm still starting from here. If I do the inverse first, that means starting here I swap the position of x and y. 0, -3. Swap the position here, I get -3, 2. And swap here, I get 2, 3. And then we do the vertical, which means flip the signs on all the y coordinates. So here 0, this becomes +3. Here we get -3, comma, this becomes -2. And here we get 2, comma, and this flips to -3. That's our result if we do the inverse then vertical way. And look at that. The points come out exactly the same. So another one showing you can switch the order, but it's going to change what transformations are necessary. Let's see, try this a couple more times and see if I'm getting any better at it. This time we're starting with f of x, this original arc here, and they want us to get to x equals negative f of y. Now, it's fine to write this, but for our purposes, we want this negative sign to be right on one of the variables. Remember that we've been doing stuff with like x becoming negative x or y becoming negative y. We can't really do that with a negative in this position. So the way to approach this, in my opinion, is multiply both sides by -1. So you get negative x equals f of y. That's better. Now this negative belongs to the x variable. That's going to make things easier in a minute. So, two different ways that we can get from here to here. Oh, sorry, this has to be y equals f of x or it doesn't work too well. One option is we could swap x and y immediately. X exchange with y, and that gives you x equals f of y. And then we could say where this x is, I actually need negative x. So the notation is pretty straightforward. X turns into negative x, done. The other possibility is we could say, all right, I need a negative out front here, so I'll put the negative on the y. Where there used to be a y, there will now be negative y. After we do that, we have negative y equals f of x. And now I must swap the positions of x and y. X changes places with y, and after we do that, we get negative x, there it is, equals f of y, there it is. So those are our two paths, and they end up the same way. This one I would call inverse then horizontal. And this other path where you flip the y's, that's a vertical, and it's followed by an inverse. Okay. Either one can work, they're both equally valid, and if we follow how the graphs work, this one I think I can sketch with something like accuracy. Starting from this curve, if we do the inverse, we get a curve that's still on the positive side of the axis, but it's flipped this way. Then we do a horizontal reflection. So instead of this thing being to the right of the axis, it ends up to the left of the axis, something like this. That red is our endpoint. If we go the other way, vertical reflection would mean we start with this bump and we vertically reflect it, meaning instead of an up, it's now a down. And now we do an inverse, meaning we flip this across y equals x. You end up on the same side. The point 0, 0 stays 0, 0. The point 5, 0 becomes the point 0, 5. There it is. And this, which is roughly like 2.5 minus 2, becomes the point minus 2, 2.5. So you really do end up on the red curve, whichever order you take this. And last one. What do they want from us this time? Starting with y equals f of x. They want us to go to x equals negative f of y, which is the same task we had last time. We're just doing it with a different function. So, as before, two orders we could use. We could swap x and y, which would land us on x equals f of y. Oh, sorry. As before, this negative belonging to the function is not really what I want. If we multiply both sides by -1, we get it over here, which is more useful to us. I notice that because what I want to do now is change my x to a negative x. Horizontal reflection. So, started here, inverse gets us x equals f of y. Then we say where there used to be an x, write negative x instead, and boom, this is what they wanted. So that's one path. The alternate path is, we could say, I want the number out front to have a negative on it. So where I used to just have y, I will now say negative y. That gets me negative y equals f of x. And now if you look at this and say, what else do I have to change to get from here to here? You'd say, I have to swap the positions of x and y. X trades places with y. And if we do that, we end up at the same end point. So this first way was swap x and y, that's an inverse, and then do a horizontal reflection. Inverse, then horizontal. With this path, we did a vertical reflection where we changed the sign on the y's, and then we did an inverse. So vertical, then inverse. So do those both do the same things to the curve? Let's check. The original curve contains the points -3, 0, uh, 2, -3, and this one is 2, 3. Sorry, 3, 2. So if we invert these, that means the x and the y trade places. And then we do a horizontal reflection, which means the signs on the x all flip. So 0 doesn't have a sign, there's nothing to flip, nothing changes there. That point is invariant under horizontal reflection. This one becomes +3, 2. And this one becomes -2, 3. So that's our finished version if we do the inverse and horizontal. What if we go the other way? What if we do vertical, then an inverse? If we vertically flip these, that means change the signs on all the y coordinates. First point, nothing happens. You can't flip 0. This one flips to 2, 3. And this one flips to 3, -2. So nothing's happening to the x coordinates, but the y coordinates are changing signs. And then we do an inverse, so we swap the positions of x and y. 0, -3. This one becomes 3, 2. And this one becomes -2, 3. And if you compare those two, all the points match. So the end message is if you have to do an inverse along with some other transformations, the order of them doesn't matter, but be aware that if you change the order, it will change what transformations you actually need to do. So you and a classmate might do this problem in 2 different orders and you'll end up getting substantially different answers. But if you're careful and follow the points and summarize the effects of each of your transformations, you should find that you landed in the same place. Hope that helped.